Just put some funny names there if somebody puts your name there.
Probably. I was going to ask.
See, I think to get access
Oh yeah,
to
so
the
there's
materials.
a key in there. So, just shout at Elliot to come and tell you what URL he's going to use because you don't have a tool. So.
What's the start? No. I can't sit down. I'm trying to be there.
All right. Can you change the title? And then put it after only on the drum. And the meeting. Wait. We should be thankful that he volunteered.
I have a feeling that he will require me to do something in common.
He's really nice.
Having this kind of tool.
So it's Teep and Jabber. Oh, okay.
All right. So it's 3 minutes past already, so I think we are getting ready to start.
Hank. Yes. Oh, nice to meet you. Okay. Oh, yeah, I've been around.
All right, so this is a TEEP, both Trusted Execution Environment Protocol, and I'm Tero Kivinen, and this is my co-chair.
I'm Nancy Kamwinjit.
This is the note well, and you note it well or probably already, so no need to go through that. And so the agenda is something that we have here. We have a problem statement, then we have a couple of examples of TEEP environments implementations, And then we have use cases and architecture, and then in the end, if we have time and if we have decided that we are actually going forward, we have some time for a charter discussion, or at least think about which parts of the charter we should include, what we should include in charter. Anybody has any comments about the charter? Oh, sorry, agenda? The blue sheet should be going around, and we have a minutes taker, and we have a chapter scribe, so everything should be set. Oh. So actually, this is actually not the. Then let's go to the overview. Yeah. So this is Hannes going to be presenting the overview.
Test. Okay.
Go ahead. You have 15 minutes.
Perfect. Yeah, I have the pleasure to start sort of providing you with an overview and jump a little bit into ARM's implementation of these trusted execution environments. And David Wheeler will speak about some other implementations of these DEs based on what Intel has been doing. Okay, next slide. Or do I have a clicker?
No.
Okay.
Oh,
I mean, it's fairly short. I want to keep it brief and to the point, and I'm hoping that you have some questions. Before or when we announced the BOF, we also posted some material to the list, and some of you may have actually clicked through the links and downloaded the specifications. But in case you haven't, I prepared this sort of high-level overview with the intention to explain you on like what are these trusted execution environments, and what is the problem we are trying to solve here. And then if you think that that's indeed a problem that needs to be solved, then subsequent question is this actually something the IETF should solve, or is this a problem for a different body? Okay. So if you look at processor technology today in terms of hardware, it has a couple of different isolation concepts already for a very long time, and you're obviously using many of them. Memory management unit, or some of them have memory protection units. If you look at more smaller microcontrollers, there are these concepts of user and kernel space to provide different privileges. Later, the virtualization concepts have been added, and so there's a lot of sort of security functionality to isolate and sandbox specific environments, with the intention that some parts of the code have more privileges, and typically they are more security sensitive. They receive more review than code that runs at lower privileges. And a couple of years ago, the hardware manufacturers came up with further concepts, and they are still obviously sort of developing new security and isolation technologies to meet sort of current needs, like with more the distribution of applications to, for example, to the edge with OpenFog, or with some of those virtualized server environments. And one of them is what is called these trusted execution environments, where you put a normal sort of so-called rich execution environment, where normal operating system runs alongside these the DE. So and I have a graphical representation of this in the next figure, so you get the idea. So this DE sits alongside this rich execution environment, and it's sort of the area where you have some code running that has certain or higher privileges. So let's jump to that figure. So here's this sort of separation. So on the left-hand side, in the red box, you see sort of the ordinary isolation techniques being used. In this case, for example, based on a Linux operating system, it's a fairly big operating system, and you have a hardware platform in between that provides this this DE environment that then, as the arrow indicates, allows the transition over to this trusted execution environment where security-sensitive code resides. And there's a separate OS running, typically, and also applications. So the terminology is not mine. That's something that is other organizations came up with, such as the Global Platform with their documents. But But the important part is that these two sort of run next to each other, and there's a transition that happens when the rich execution environments, for example, in case of a banking application, needs to have access to some credentials. It swaps over to the other side involving the hardware and does whatever it has to do, whatever that specific application does. For example, it may also involve a trusted UI, so that only the trusted execution environment can write to the user interface. So there's that's sort of the rough idea. So if you find these concepts being used, for example, in your mobile phones and tablets, but also in hardware like your home routers, or even the latest version of Raspberry Pi has such a technology built in, although a somewhat bad implementation, but it nevertheless in there. Okay, next slide. This is a reference from the global platform specification, or DE system architecture document. And what this, don't ignore the details, not that relevant for this overview, but what it's trying to illustrate is that this the DE concept is a little bit bigger than what you are probably known from a, let's say, something like a smart card, where you only have specific cryptographic functions and credentials being sort of encapsulated and secured. But instead, this the concept extends to the memory, extends to the bus, and even to peripherals. And the example that I mentioned beforehand with a trusted UI is such an example where this trusted execution environment extends throughout the whole system. Okay. From a software architecture point of view, there is, in the previous diagram, I showed this, the platform on the bottom, and sort of the arrow going from the rich execution environment all the way to the trusted execution environment and back. There's obviously some APIs and some hardware mechanism to enable that transition, and there's sort of a message passing interface that has been defined. This is something the global platform has standardized as an API, because you need to go through this transition internally within the CPU, within the software stacks, because you have nevertheless two operating systems involved here. So there's a lot of sort of going forwards and backwards through the stacks to actually make this happen and pass the messages around. Again, ignore the details. We will go into some of them a little bit later on a high level, but for the purpose of the profit, I think it's the most important part is the fact that it's just there's a transition happening. So the DE is actually not just sending messages on its own. Basically doesn't have the internet connectivity, so it sends it. It's not a multi-core processor that just acts totally independently. I think that's an important aspect here. Okay, next slide. So these technologies the concepts have been worked out, and also implementations of these concepts, and even hardware manufacturers develop the chips, and you have the chips actually in your pockets and in your hardware presumably sitting in front of you. Unfortunately, there's also the challenge that you have to provision software into this trusted execution environment so it actually does something. Otherwise, it's just a piece of hardware. And today, this is done in using proprietary techniques. And as it is often the case with proprietary techniques, people are a little bit reluctant to then use the technology. There's fragmentation in the market because there are different proprietary techniques, not just one. And so the consequence was that the uptake of this technology that could be used for different use cases, from banking to different authentication mechanisms and so on, and even for some of the security technologies that are being developed here in the IETF, has been somewhat limited. So the goal, our goal, and why we came here to bring this to the IETF, is that we thought, oh, wouldn't it be great if we could develop a standardized protocol instead of having these proprietary mechanisms to be able to load and manage the software on this trusted execution environment. And needless to say, if you have a mechanism that installs software that updates software, that deletes software, and all sort of the concepts, the management around it, that needs some security, because otherwise you can easily imagine all sorts of bad things happen. And so that was also the reason why we thought that this is a topic for the security area to look into, not just because the isolation concepts on the hardware level are typically understood as security concepts and useful to understand as a background, but also the protocol itself has a lot of security aspects sprinkled over it. As in case you have read the document, the specification, you will see that there are those security mechanisms there.
Mohit, could you go back to the previous slide? So, Mohit, M-O-H-I-T. So applications have to be provisioned somehow on the TEE. So is it like I'm a developer sitting in the basement, can my application be provisioned? Or is it only some trusted applications that can be provisioned on the TEE? And what makes application trusted? Like, can anyone sitting in their garage have like access to the TEE? And
I will get to them and sort of envisioned sort of user or developer experience in a later slide. But of course, it depends a little bit on what hardware we are talking about. For example, in the Raspberry Pi case, the Raspberry Pi I've been using, I could hack around whatever I want. Like it's just a very open system. There are also some other, so there's, for example, the USB Armory, which is sort of a Kickstarter project that also has the trust zone component there. You can add whatever you want. It's open, but of course you can also, like with many other things, you can lock it down if that's something you don't want. It's similar with many other IETF technologies. You can buy routers that are where you can install your own software, whatever you want. And in general, it's not related to security technology. When I bought Linksys routers, you could update whatever you want as long as you had physical access to it. But the others where this is not possible. So it's very much the same here. Whether you can root the phone in the phone case, maybe for some phones, maybe not for others. Does that answer the question? It's nothing technology-wise. What we are doing here is nothing in there that sort of locks you into doing one or the other way. Okay. So coming to so if you believe that that's a reasonable, so there is a problem there. What does it actually mean from an IETF point of view? And I'm getting back again to this figure that I had shown previously, but this time sort of illustrating the communication concept, because we had put together sort of a strawman proposal, what we call the Open Trust Protocol. And you can argue about this name trust all over the place. Always, I don't know, I didn't come up with the name, but in any case, it's a messaging protocol that uses Jose and JSON encodings to pass messages back and forth between this sort of a client implementation of this in residing on the TE on the trusted OS, talking via the rich execution environment, as I had previously shown with this message passing concept, which is sort of a little bit abstracted here, to some component in network where the software actually comes from. And there's a little bit of back and forth because there are a few functions, as Ming will later explain, on giving, of course, you want to, the DE wants to authenticate that it's certain that it talks to the right trust application manager, vice versa. This DAM also wants to make sure, the server side wants to make sure that it indeed talks to a specific piece of hardware, what some people call attestation in this context, so that this gray error, this messaging protocol on a gray error that in this strawman proposal uses the JSON-based encoding is what we are trying to define here. Good. Okay. And go ahead.
On the previous, Karen Watson, Juniper Networks, previous slide.
Mm-hmm.
So typically when you're provisioning a application or onto a router, the app, and it may also have to provision firmware like into the forwarding plane. So the application would bundle the firmware image as well, and then it would delegate the firmware image into the forwarding plane. Why wouldn't a model like that work here?
So the main use cases, as the Peng will explain later, in our case, was focused on the deployed market where we have mobile phones and tablets. Those are the main sort of target areas for that use case, simply because there's a lot of hardware already out there in the field that we could enable by doing that. Whether there are potentially some other areas where, like routers have such a trusted execution environment, which I don't actually, I'm not an expert in that.
I was just using a router as an example, but I mean,
do they have
think of the
TEs?
phone is like a router, and so you're provisioning an application to the phone, and then it could, inside that application, could be the firmware that goes to the TE.
Okay.
But you know, why couldn't you use existing mechanisms for application deployment? And then distribute
actually, I will interrupt. I think it would be better to have the actual questions later in the end, but because there is 3-4 more slides that will actually probably answer some of the questions, and if there is still some questions open after that, then we're going to have a guest questions after that. Unless there is a clarification question about something in the slides or something that is not about the protocol, but it's not what is happening there.
Yeah. I'll give a very quick answer to that question. Yeah. So Da Peng. I think the model that the previous speaker raised that. Sorry. The disadvantage that is that you need to update the whole application. But for example, in some scenarios, for example, for the payment application, only the fingerprint part is running in the trusted execution environment, not the whole application. So from the application developer perspective, it's more easy for them if we can only update the fingerprint if needed, not the whole application. Otherwise, the user will not happy. You have to download a huge application. So, thanks.
Right. Okay. So we'll definitely discuss this a little bit more later on. So Mohit asked about this sort of experience. So here I have a slide on what I consider the envisioned user experience or developer experience. So on the left-hand side, you have an app developer who writes an application. He actually writes two components of it. One is the application that resides on Android and is distributed using the ordinary Android app distribution mechanism. But he also then writes a component that goes into the TEE, which imagine a banking application that specifically has the OTP generation as an example, as one authentication mechanism used in the banking sector residing on the phone. So that may be a component that goes into the TEE versus the rest of the application, the UI and sort of all the other the account management stuff would just go into the into the normal Android application. And so the app developer uploads in step 2, uploads the Android app to the Google Store, for example, and the trusted app, as it is called, to the DAM. When and it sits there. When users then come along and decide that they want this and they like the permission that the app has, then they go and install the ordinary Android app. And banks, for example, in this case, have specific requirements on what hardware they want for their environment, so they don't randomly install it on anything. So if someone comes along that has a phone that has no such execution environment, they may just fall back to some other authentication mechanism. But in case if they have such a technology, would go and download their appropriate binary from this from the DAM and install it and then make use of it. And obviously there's some authorization involved in the steps 3 and 4. And then finally the user uses it. That's sort of the idea to provision some of those applications. Okay. That's sort of my high-level overview. I hope you found that high level enough to be useful, but not too high level to be useless. There was, I had included a couple of references, so in case I posted them already to the list, but if you want to take a look at the Glory details, so obviously there's a longer specification, and specifically when we come to this, the implementation and realization of the abstract concept, then there are even more details. Okay. Yeah, so, and we have 2 short presentations, very short, about the realizations of this abstract DE concept based on what we do at ARM and what Intel does. Next slide. Our implementation is called Trust Zone. And to understand that concept, I thought I would spend one slide on our sort of architecture as it is used today. We have different profiles for different use cases, and it partially answers also the question that was previously asked about why can't we just use some existing software update or firmware update mechanism. We have these application processors which you find on your mobile phones and tablets, etc. We have something called real-time profile, which is used in, for example, hard disk drive, something that requires, has tight constraints regarding real-time behavior. So you find those in cars, for example, or hard disk drives. And then there's the microcontroller profile, which is what we typically talk about in the context of IoT. These are tiny microcontrollers. And this latest architecture, in our case, they always have these funny names. In this case, ARM v8m. That was just recently published, so there are no chips available for that yet. This includes now Trust Zone support as well, but the whole architecture works there very differently. So it's actually our envisioned use case for what we are talking about here. This BOF is mainly for the A-class processors. These are more powerful processors, as I said, in mobile phones and tablets, not for these other things. Okay. And not very surprisingly, the figure looks again very different, but just now the names, the terminology is a little bit different. So we typically talk about normal world and secure world instead of REE and DE, and we use a sort of secure monitor. That's another layer. We have some open source reference implementation called ARM Trusted Firmware that plays the role of a secure monitor, and we also make an open source stack available that people frequently use for the secure OS and the secure world, which we call Opti. You can check this out at those GitHub repository and run it if you want. And it's available for some time already. It was an extension a couple of years ago to an older architecture, and has been available since then. So that's pretty much all I wanted to say about that. And feel free to come to me afterwards if you want to know all the Glory details about how this works, or point us to some documents or tutorials. We have several day tutorials on this. As you can imagine, there's a lot of details on how to program these or write operating systems for this. Okay, look at the references.
All right, so then we have
Trying to get hold of David.
Then we have David from remote talking. So if you can get to I think it would get to the Meet Echo queue, and I can first get you presenting.
Can you hear me in the room?
Yes, we can hear you.
Oh, great. Okay. So we can just go on to the next slide. The first thing I want to talk about is that there are variations in the TEEs. TEEs are typically available to provide some sort of protection that isn't normally available in the rich OS side or on the normal programming side. And oftentimes those protections have to do with how big the trusted computing base or how much code and hardware have to be trusted by the developer. So as the TCB grows, there's less and less trust, right? Otherwise, we would just use the environments in the rich OS. We would use the process protections and rings and other things. But we found that those are able to be attacked. So there's some reasons to say I want to separate certain functionality that's much more sensitive off in a special type of container, a special type of execution container. And so oftentimes we want to get better confidentiality of our code and data, maybe additional integrity for our code and data, some type of confidentiality for execution so that other applications can't see or interfere with our code. And oftentimes there's some coverage of attestation. How do you prove to other parties that your code is trusted, hasn't been interfered with or infected with malware? And so all of those things, there's various levels that we could go to create a TEE. Some TEEs are very small, and they can only handle very simple operations. Others are much larger, and the design requirements that are applied to a TEE are dependent upon some of these kinds of requirements. The other part that kind of gets into some of the variations of TEs that you might see between ARM and Intel and others is the type and capability of the root of trust. So is the root of trust verifying code, or is it merely verifying the platform, for instance? Can it attest to the TEE firmware, or does it also attest to the code that's running in that TEE? And then can that root of trust be used to derive other key materials for the application or for other usages? And then the last point here is anonymity. There's all different levels of anonymity that can be provided. There's different types of anonymous type protocols and algorithms, and you get varying degrees of anonymity depending upon the protocol and the algorithm that you choose. And in some cases we want to preserve that or provide the ability to preserve that. So these are some of the requirements and variations that Intel sees when we build TEEs. If we can move to the next slide. So Intel has several trusted execution environments that are available in chips today. I think the one that we'll probably spend a lot of time talking about over the next months, if we approve this charter, is software guard extensions, or SGX. SGX is really different than the ARM Trust Zone case. Instead of having a set environment or a secure world, you have the ability to set aside some memory, and then you have CPU instructions that enable you to, on the fly, instantiate a trusted execution environment for a piece of code. And that trusted execution environment is linked to the process. It's in the same virtual address space as the process that launched it. So much like someone earlier today was talking about, why can't we put the trusted code in with the application and just ship that along. In fact, SGX is one of the ways that one of the things that actually does that very thing. So you have a full rich OS application, and part of that application is a DLL type attachment that is your trusted code, and that gets launched inside what SGX calls is an enclave in separated memory. And you know, there's different perspectives. Is that good or is that bad? You have to. One comment was made that you have to update the entire app in order to change the trusted piece, and that's true. You do, in that case, have to update the whole application. But I think there's an experiential side that says, if I'm updating my trusted piece, most likely some of the interfaces, parameters, or linkages to my untrusted piece are going to change as well. So SGX is different than Trust Zone, but DAL, or the Dynamic Application Loader, is in fact very similar to Trust Zones in the case that there's a specific secure world. In this case, it's a crypto processor that's separate, but it's on the same die as the CPU, and it has a small OS, secure OS, running inside of it. And if your code is signed by the proper key, you can load small applets into that environment, and they can interact with multiple different applications. They're not tied to the process that loaded them, as in the case of SGX, but it's much more open. The Intel Innovation Engine is a similar type of environment as the DAL, except that the only thing that's really provided is a firmware environment, and most of the time Intel only allows OEMs or ODMs to load programs and things like that inside there. But these are all different types of execution environments, and there's others in the chips, but these are some of the big ones that I think are worthy of discussion here in this group. So let's go to the next slide. So this is showing a little bit about SGX, and I don't want to belabor talking through SGX at this point, but we may do so in future meetings. I do want to point out the link there. I provided this mostly for those who are more interested in looking at this later. The public material on SGX and how it works is provided in that link. You can go to the next slide. So some of the interesting attributes I think that SGX has that may be different than Trust Zone is that the enclave can be constructed and loaded on demand. So as an application needs to use the TEE, it's able to use some special instructions to actually load that TEE. The launching process is verified by what we call the SGX launcher, and that verifies the trusted code to make sure it's authorized to run on the platform. So in some ways, the SGX launcher operates as the TSM in the protocol by verifying the appropriate authority to be able to load an application into the TEE. And so this is a very interesting point I think that we should talk about, is that the current proposal on the table includes an external TSM that is the trust manager for the device. But it doesn't necessarily have to be that way, and we might want to talk about ways of creating specific service access points or trust points, and those can float from the device to some network infrastructure depending upon the ecosystem and the device itself. Another thing that's interesting about SGX is that we use the root of trust material to derive keys specifically for the enclave. So each enclave has their own private derived key material. This creates the ability to cryptographically bind secrets both to the platform and to the trusted app. And there isn't a way for apps to accidentally share that information. So in the case of trust zones, there's often the requirement to put a small OS in there to arbitrate between apps and make sure apps have access to only the capabilities that they're allowed to. SGX provides that separation by default, and certain protocols for trusted sharing between enclaves is required in order to share data between those pieces. Now, I'll point out that the DAL has the DAL TE that Intel has is very similar to trust zones and has to use an OS to create that separation. So my point here is not to lift one TEE up over the other, but to say that there's different variations in the way that you can build TEEs, and they have they have value to the marketplace. And any protocol that we put together, we need to think about supporting those things and how we best leverage the needs of the marketplace into the protocol. The last thing that I'll point out from the SGX side is one of attestation, that the SGX enclave can be attested to by the root of trust of the platform, but the application doesn't have direct access to that root of trust. And that attestation can provide complete anonymity to the attesting application. And that's one of the attributes of the EPID protocol and algorithm, which is part of Intel's root of trust. Okay, we can go to the next slide. Oh, one more point on that previous slide. If you're interested in the deep details of SGX, on that previous slide I had a link to an academic paper that goes in deep depth into SGX, and I'd refer you to look at that for all of the nitty-gritty details. So as we in the birds of a feather, we look forward to getting a charter. Some of the things that I think are important for us to consider is that we need to support different types of TEEs, and we need to look at supporting platforms with multiple simultaneous TEEs. Some of those may be cooperating, some of them may be non-cooperating. And we need to look at supporting the validation of the TEE by cryptographic means, not just by organizational or third-party type setups in the protocol. Privacy is also extremely important, and for that usage, I think EPID is extremely important. And then to sum up, I think we can have discussions about is this necessary or not. In some of Intel's TEEs, like SGX, there isn't really a strong need for an outside manager, but I think that there's a benefit to the marketplace to create a better uptake of secure applications that utilize TEEs, all different kinds of TEEs, where a protocol that IETF supports would become very helpful in increasing the use of more secure areas of our CPUs like TEEs, both TrustZone and SGX and others. And that's all I have.
Right, thank you. So,
just a point of clarification.
Yep.
It's Elliot. Thanks for your presentation. I just had a quick question. You said there may or may not be, I'm trying to repeat your words clearly, there may or may not be a need for external services in the context of TEEs. Can you just expand a little bit about what you meant by that?
So my viewpoint here is that in the case of, for example, SGX, and the point that another gentleman made earlier, where the trusted application can be embedded into the untrusted application or the normal rich OS application, and delivered as one group to a platform. In those cases, you can use current infrastructure and protocols today. There are device management protocols. There are people are building things on top of HTTP and HTTPS. So I don't think there's necessarily a need when you look at it from that perspective. But when you look at other types of TEEs, specifically, TrustZone or Intel's DAO or others that have maybe a more difficult way to get trusted applets into them, I think a protocol is helpful. And then, my point is that even though we can point out cases perhaps where a protocol isn't necessary, creating a uniform way to get access to those trust services, I think, is of benefit.
Okay, so then we move to the use cases.
Okay, so I'm going to talking about the use cases of the OTRP protocol. As Henny's presentation, we already have the TE environment in a lot of handsets and in, for example, in mobile phones. And there already have hardware chipset can support the trusted execution environment. And actually, there are already some deployment applications already use the TE environment. That is, for example, in the payment industry. As an example, in China, there are a lot of mobile payment applications, including from the banking industry. The banks can provide the mobile applications to the users. Then the user can just use their phone to do transfer and other financial services. And even for the third-party payment providers, for example, as one business unit of Alibaba Group, we can also provide an Alipay service. So that is actually is an application that can running on the user's phone. And nowadays, we need a better and more secure ways to protect the users' credentials and other security data. So in that case, most of the payment applications use, for example, fingerprint to protect for the authenticity of the user's identity. And if the fingerprint can be ran in the trusted execution environment, it would be more secure than just running as an ordinary application in the user space. So that is a major use case. And why we need protocol to provision that. I think in previous discussion, someone point a good point. Why we should not just use the firm update. I think that Dev also explained that a little bit. There are different implementations of the TE technology, and we need a standard protocol that can interoperate between the different players of the ecosystem, and can also support different types of the TE technology. So I think that's very important. I think IETF is also the right place to do that. And in this particular example, I think the server side can provide the ability, for example, the identification I just mentioned, and also some applications also use the security user interface. For example, for some bank application running in mobile phone, they use their own keyboard. It's not use the operating system native keyboard because they believe that it could be more secure. And that keyboard application could also running in the TE world. So, for example, when the application provider sometimes need to update their trusted application, there will be a need from the server side to do the application update, or they even want to install a new application on the user's phone. And in the ecosystem, sometimes it's very difficult for only the application developer. It's very difficult for them to deploy the trusted application into the TE world. Because in some cases, they need the help of the OEM vendors. It's kind of different from the normal applications. Even for normal, for example, Android application, you need to distribute from, for example, Google Play or other application store to distribute your application. And for the TE application, it could be more restricted conditions. Then sometimes you need to go through the OEM's channel to install or update your trusted application. In that case, it will be cost a lot of efforts and the delays to update the trust application. So if there is a protocol that can run across different vendors and can run between the TE world and the server side called TAM, that could be much easier for the developer to deploy their trusted applications, to install, update, delete their trusted applications in the TE world. Okay, let's move on to the second use case. I think this is already also happen in the real world. That is enterprise authentication. And it's very popular today that the enterprise allows the employees to use their own device, bring your own device. It's very popular. And there are many very sensitive enterprise applications that could be running on the employees' mobile phones. For example, the VPN client. So there are many sensitive data, credentials could be stored in the user's normal phone. For how the enterprise can make it more secure. So TE is a very good solution. You can store the sensitive data, the identification credentials, and also the personalization data into the TE world. And in that case, the enterprise also need a way to, very easily to update, to install or delete the trusted application, and without the help of the OEM vendors. Maybe sometimes they also need the OEM vendors, but it's based on different configurations. I think we can discuss that later in the architecture or in the solutions. But I think that's the major two use cases that already happen in the real world, and we have a lot of use cases that in our mind, but I will not discuss today. Hope that two use cases can help the audience to understand why we need this OTRP protocol. Thanks.
Okay, so that's then let's move to the architecture. We are a little bit late, but hopefully we can. Yeah, we have some, but I actually want to keep the discussion, have time for discussion also.
Hi.
No. Stand on the big
Stand by the
pink box.
You're being recorded.
There's a rule here. Okay. Me from Symantec. This is talk about the architecture, also introduction of the Open Trust Protocol, Hannes introduced earlier. And we have after draft 03. Just a quick service, how deep I need to go. Richard, how many people have seen that after draft? Roughly get. Yeah, few people, majority not. Okay, majority not. Okay, thank you. So starting with a quick check, give a little bit of stakeholder here, the ecosystem, why we need such a protocol. You can see here, the middle two is really, we have device manufacturers, you have trusted applications, then you have a service provider, you have applications, right? They have the end-to-end relationship, right? You have service provider want to manage the applications, well, better it's spread out, right? In many devices, you can utilize the secure hardware. So then they have this kind of multiple parties in this. They have multiple TE providers, as David just talked, right? We have Intel, we have the ARM architecture trust zone. Then you have the hardware, have chips, and have a firmware, different firmware, and may not even have firmware. And in this ecosystem, right, we look at a way how do we grow the interoperability to spread, right, the trust application adoption. So next. So in this, we want to build establish a trust, mutual trust between the trusted devices and a service provider. Goes through a trust application manager. A few quick high-level decisions were made during our design. First one is that we will use PKI as asymmetric key, right? certificate is and on, right? But it's a PKI instead of symmetric key. So where you can remotely validate the device or remotely validate another party, right? PKI in this and with certificate. That's one main choice. Second one, now you go to they will stay at message level, right? Between device and a manager, it's a remote server provider or the trust application manager, a server provider users. We define the messages, right? How the network communicate is open, right? Up to them. So we just make the message. And for that message, we say, okay, we start with JSON. It looks like quite lightweight. This is also RFC spec, which is reuse that one. We do not reinvent things. Right? But there's some input coming in. So what better serialization and the encoding makes it more compact for IoT devices. Those can be expanded or further work in this work. If this gets to the work group, right? But this you need start with the JSON. And then that defines the signing, encryption, all those standards already there. That's a very good one. That will pick that as a candidate, right, in our design. Third one, now we define the message protocol. I'll talk about next. Define a message between device and remote manager. Within device, you have many normal apps, like Android normal app, okay, normal apps. You want to communicate with the secure word, TEE. We don't want every app knows how to talk with TEE. That's too hard, right? How to deliver a message there. So we need a little agent. We call it Open Trust Protocol, OTRP agent. That agent has standard API so that rich side applications, Android application, normal word, not only Android, I just talk about normal app can access trusted applications through a standard API. So that's the goal. Okay, OTRP agent is needed so that it can reduce the work for rich apps. And further, to make the basic assumption, we start with say, assume device has one TE. It's a very rare, we did a survey, very rare, a device has multiple TEs. The protocol support multiple TEs, but a given device, we just simplify. So let's assume it work with one TE. You have multiple TEs, now you start to get much more complex. That's not a common. Okay. Next. So this gives you a high-level view. So this device side, we define the message protocol between trust application manager, TSM and TM. This one and the device. Okay, this is JSON messages. We define 7 operations, 7 messages, but more like a regular, you can imagine, CRUD functions, right? Create, update, delete, and a query. It's really common to manage a trusted application in this one, right? There's a message defined way how to manage that. You want to do that, and server providers, they will create those applications, right? Server provider create a normal app and a trust app. May not belong to the same vendor even, right? You can use other trust app, right? So Darpin just mentioned, that's merely just a core function that needs security, needs secure storage, right? Doesn't need to be full app. So it may be across different providers even. So that application sign, as we know, is very common. You signed, and TSM, how does this TE allow anyone to update your device? That's a dangerous thing, right? You need to trust which application manager can update your data. Well, user can authorize it, or by out of box by manufacturer choice, enterprise choice, bunch of trust scheme you need built in. What the TSM you trust? Okay, they get a certificate. That's a more common, right, for the identity. Now, device side remotely, I deliver my application to a remote device. Which device do I accept, right? What kind of TE, what is the firmware I trust? That's a device. I want my application to be deployed, right? So that you want to have that one. It's a device attestation. This one tells the remote TSM my information, what the TE runs, what the firmware runs. So a service provider or TAM can decide what is acceptable to them. So they have a trust anchor point. So that's the high level, the scheme. So they have message protocol and OTRP agent. This is a software interface here. It's API interface we define. That's 2 pieces in the scope. Next, please. So that's just touched upon a little bit already. So OTRP agent, I guess for rich app, Reach app responsible talk with TSM. Whether you go to HTTP, whatever protocol, network protocol, your choice. You just need to change message to the TSM. The messages are signed and encrypted end-to-end, so that there's no man-in-middle attack here. So TE, the device, TSM messages are mutually signed and encrypted. So this one just purely a black box here, just relay. So rich application, say I receive message for TSM, say TSM is an update application here. Okay, rich application say they need to deliver a message TE. How to deliver that? Through an OTIP agent. This one usually offered by TE vendors. They know how to talk with their TE, right? So that we don't define that part. So we just need to define the trust point. Well, how the TE and TSM, they can trust each other. Then have this one interface to how to deliver that message to TE, so they can further utilize that. So this will give a little bit of list of what to establish trust between device and the TM or service provider. You can see for TSM side, TM side, right? They trust. They have trust anchors. It's really say certificates. So in this one, we choose to use say certificates. Right? They have their own key pair, of course, like a server, right? They have a key pair. They also trust the point. What the TEs they trust. They make accept certain TE, not others, based on quality, based on region, based on policy, whatever, right? Also firmware, right? If that firmware information is given, right? So what's the accepted device? What device they trust? That's for TSM side. For the device side, they have each device has two. If you have firmware, what depends on TE, that firmware here, what ensures secure boot, right? Device boot from is to check the TE is junior, right? TE itself is signed, right? That's the secure boot part. Secondly, when a device delivers information, after the information to a TSM remotely, it tells who I am, what my TE is, and what my firmware is by a signed piece of data, right? Based on proof possession, based signed data, that information sent TSM so they can establish trust. And you have the CAs. The CAs can be different, right? Different places, different regions. They issue certificates for TSM, TM, and server provider and devices. Those can be distinct CAs in different regions and different places. So I mentioned this earlier. It's just to repeat that for the highlight, the scope is really define message protocol between this is device and TM. This message protocol here and this OTIP agent. Right? The others are this just interaction, right? You do get a certificate from one of your picked CAs, right? One picked CAs, and that is outbound. What had happened, that's not specified in this protocol. This protocol really defines trusted messages. Yeah, does this give just brief go into the entity relationship and say one device over here you have one TEE and well one TE end-to-end relationship. One TE can be managed by many TAM and one TAM can manage many devices, many TEs. Okay? And one server provider deliver many applications. Well, they can own multiple secure domains. Within a device, a TE can have multiple secure domains. And trust application today, well, by practice, they reside inside the secure domain, which is isolated, right? The reason for that, secure domain is isolated. So trust application, multiple trust application within one domain. Mostly the one domains belong to one of the service provider. Okay, this is a quick relationship. This is sample flow. I think a little bit more technical. The diagram kind of showed earlier. It's really the flow is like this. In the beginning, you have an application. Your application started with I need to use a trust application. First thing I will check, is the application already in my phone or in my device? It's not there, I want to install it. What you do, that application you talk with the TSM. TSM is say, I want to install application, right? Go ahead, send a command to install. Then you go to TSM, send a command, say query, say, they would query query device, send a message. The JSON message is signed by TSM. Send by TSM message, and they come in here, say, tell me what you are, right? And then this send it back. This is called device information, okay? It's a device state information. This will be signed and it can be encrypted because the TSM send a public key. Once you trust, it sends back a data encrypted and signed by trusted firmware and TE. So now this is actually TSM decided, good, this is a good device because follow my policy. I will accept that device. I will deliver the application to it. In this case, next step, if the first time, it will create a secure domain for that service provider. So it creates a secure domain command. So now TE will verify, again, this is TSM, it's a trust, and it will create domain, return domain is created. Next step, you just say install app. Now it's deliver trusted application through it's just a blob, right? Binary signed JSON message coming down, and the personalization data, right? Trust application usually have personalization data. You also put it together, encrypt it, okay? Encrypt it by, in this step, you already have trust domain. That secure domain already have private secret key. You can encrypt in this established. So now encrypt data all the way down here, and device will be verify this one, decrypt data, and install app, and personalize data, and finish, send status back. So that's just sample quick flow. Any questions?
Okay, now I think it's a good time to take a questions and something like that, so discussing about this.
Okay, Ben Kaduk, and I don't see DKG in the room, but I think it's probably worth saying that, I mean, you were talking about how we can have this sort of interaction between the TE and the TSM. It's like a black box, so the regular application can't see what's going on. And that opens up the possibility for a case where a user has their phone, their device, and there's some code running on that the user has no visibility into and no control over. And that might be a privacy risk for the user. It might be something they're concerned about. I'm not going to say you shouldn't do this. It's just something we should be aware about, that there might be some privacy considerations or other considerations about having the ability to run this sort of black box code on a device that's not under the control of the end user and is only under the control of the hardware manufacturer or the OS vendor or something like that.
True. That privacy is one of the concerns. Try to address that one. Second one, so you said there. If the trust application itself can be a certain thing, right? Black box. But we do so, which is this level of trust is a device with trusted application manager, which will vetting the app, right? If they deliver malware, well, it's in secure domains isolated. The malware increase certain memory to a little bit deny service attack pertaining to the device, it's possible. But now who verifies malware? That even that whether malware, trusted application malware, possible, right? But who's vetting that? That's responsibility out of scope of this a little bit. But we do say delegate that to the trusted application manager. That may do some job.
Phil Humbaker. Yeah, the thing that I always have with these trusted computing things is that you always give me a full-featured Turing machine, and all I actually want from a trusted environment on a computer is the ability to do a private key operation on a private key that is embedded in that machine and cannot be removed from that machine. If you could give me that, I think that you would give me 90% of the security utility I think that can be gained from this. Where I get really skeptical is going beyond that, because if you're not doing operations and private keys, then what does doing that calculation in a private box give me, unless it gets through to a screen or a speaker or whatever, or take input from a microphone? And as soon as you bring any of those inside the security perimeter, then I think that your trusted environment is probably not going to be very useful anyway. So I'd like to look at really restricted uses of these things rather than going for the all singing, all dancing Turing machine that you keep giving me.
Thank you. Good input. As I use, you're talking about my application types now, right? What kind of application may be good candidate to be in that environment?
I would like to respond to Ben's comment first. I think, as David mentioned, and if you looked at the Open Trust Protocol document, it points out a couple of different privacy aspects that companies like Intel and ARM and others have worked on already, because these privacy concerns show up in different levels. They come into the form of, if you do attestation, you're obviously releasing some information about the device by design to the server infrastructure. So if you want to have unlinkability between different service providers, then there are mechanisms exist that you can avoid that linkage. And that's sort of something that this type of community has been entertaining for a while, and there's existing pros and cons that each of those mechanisms have. And it also came up on the mailing list, and it's definitely something that we need to discuss on the list. Yep. To Philip's point, I think so. What we are trying to do here is with, and that's why we work with AMD and also with other manufacturers of this hardware technology, and Intel and so on, is that we have come up with these technologies because the market has been, or companies like Alibaba and others have been asking for features that are more powerful than a SIM card, than a hardware storage, purely sort of like doing one cryptographic operation and making that available. And they are using that, for example, for this trusted display, trusted input, all sorts of different capabilities. If you want to have a different mechanism, maybe the protocol, or if you want to have a different hardware secure, target the different hardware security environment, like let's say secure elements, maybe there's also some use there with this, but the community that we have been reaching out to was focusing on specific hardware components. And maybe you bring these other guys along and help us work with them as well. And maybe if the protocol is useful there, that's even better. But we are not developing those, so it's a little bit more tricky. And specifically, the hardware aspects are important to put an emphasis on. In the IETF, we don't work on hardware. Like in the IoT case, we develop protocols that run on different hardware, obviously, but having an understanding of what the limitations and the purpose of the hardware is obviously crucial for designing something.
Yaron Scheffer, I'm wondering about the commercial viability of this scheme. As far as I know, OS providers, so Google and iOS, are disallowing applications from making changes on the fly. They want to have very tight control of what apps are installed on your device. So it seems to me strange that I will have this sort of pipeline right into the security heart of the device that allows me to change. Well, I can't change some DLL in my application, but I can change the very security, like root of trust of the application. Weird.
Yes, just a quick comment on that. All right, like even Google, that on the Google Play App Store, even those apps have multiple app stores, right? People can distribute apps in different stores. This one, the times multiple time providers. Yes, they can update the trust zone side, right? Trusted secure word side. Yes, application and more. But I think that's even today. There's already some trust applications through the trust application manager today. It's just proprietary. So what we said, it's a proprietary today. We just open this. I think open this will have a more secure and more monitor. Right? Google didn't say anything right, so far. Right? It's in field already in practice there.
In addition, so in addition to what you said, Ming, sort of using these proprietary techniques, we worked with some companies like Alibaba to have sort of customers of that technology who are interested and willing to deploy these type of things as a sort of like as a useful indication that this is not just a research exercise. But looking at some of the working groups in the IETF, we've seen other people who even talk about some of the trusted execution technologies being used in networking related purposes. And those are also use cases. So now we have a little bit limited time to discuss maybe much wider ideas that people have. Those are the things that we looked into, and I'm happy to learn about use cases that others had in I2 NSF or whatever the group's name is, and so on, what they want to do with similar technology.
Eric Nordmark. So first I want to make sure that the various documents, if you have a working group in this space, that the various documents that people would need to read, that everything is sort of openly available. Like a open trust protocol, is that something that is just freely published that anybody could read? And are there other
Yeah, it's in
that,
after draft. It's published there.
and are there other things that a working group would need to understand to be able to define these protocols? So whether it's from Intel or ARM or anybody else that people need to have access to?
Yeah, so the document, the write-up that Ming has been talking about is a regular IETF document. It's a messaging protocol. Depends on how you want to implement this. So if you want to implement this today on Raspberry Pi, you can do that. But if you want to use some specific hardware, you will have to download that specific documents. So for example, I mentioned these pointers to imagine you want to add this to our Opti as the client side of that protocol, and you will have to download that code. That's it's on GitHub. You can do that if you want. I pointed some of the documents to our specifications to the list, and you can also download that if you want. It's more background information. It's not something that you would necessarily need to implement the protocol mechanisms. Probably very similar to what you would probably more use SDKs instead. You wouldn't start to implement all the stuff from scratch. Like if you write an Android app, you're probably not going to like literally write the operating system. Hopefully not. So you would tag on existing stuff. So that is available, but it's a good concern. So if you find something that is not available, then drop us a message.
Well, but it's not about implementing, right? I mean, the purpose of a working group is actually to specify the protocol and to review it, and whatever they need to understand to be able to do that. Right?
Yeah, that information is available, and I haven't checked the links that David distributed, so I assume that those are also downloadable, pointing to downloadable documents. I don't know.
So I had one other question, which sort of relates. This is me trying to understand the big picture here, and it relates to the second bullet on the slide here, which is, so if we specify this protocol, what is unique about that when it comes to the TE, right? As opposed to it being a general protocol that could also be used for updating or downloading any other applications on the device. Because I don't understand the delineations between, sure, you might need some extra pieces to deal with the fact that it needs to go into the trusted execution environment. But does it mean that it will also just fine be able to download any app that I need to install on the device?
So that was no. I think as briefly that we didn't go to other kind of application management. Just this part is more for trust application in the secure OS side. That was the current scope. Or
would it be capable of, was the question, not whether we want it to or not. Would it be capable of? Because that helps understand what this thing is.
That's a scope discussion to me.
So I can explain. Like I looked at it. The question was obviously something when we worked on this. Could we reuse, for example, our IoT firmware update mechanism for that purpose? And that uses DLS, and it doesn't use sort of attestation concepts in a way that David or the Open Trust Protocol does. So in that sense, because it has this sort of weird sort of messaging layer that needs to hop via this relay, and so the messaging didn't quite match. So that was a problem. So we needed something that provides this application layer security mechanism. The attestation didn't match either. And so in that sense, it looked like a mechanism that is worthwhile to look into. Of course, we got inspired by what some of the work that we had done earlier. But for example, with the IoT devices, we just replace the whole image. So there's this concept of security domains doesn't exist. Loading different applications from different vendors doesn't exist either, because that's not the way how IoT firmware updates work. Maybe there are some good examples that we should look into from general application distribution mechanism where we actually can learn something. And I looked at some of the Linux distribution mechanism for some of those protocols, and there's certainly something to look into, but they often don't tend to have attestation concepts there, which made it different again. So if you have some good examples that you could drop to the list, I think that would definitely be something we should look into.
Chris Anasio, Carnegie Mellon. So as I recall from TPM, we have a lot of these same shared concepts. And I'm kind of curious in that I don't believe I ever saw a certificate authority that actually validated my TPM chip ever. So is Qualcomm actually signing up to run a CA to sign all these chips? Or like who's actually going to do that part? Because is that not a linchpin of this system?
So that's a provider question. I know for today, for certain device manufacturers, phone manufacturers, I know they have their own internal CA. Right? They do have the signed devices, signed firmware, and they have that. It's not necessarily public, but if you have multiple of those, right? Now those certificate or CA can be published. Say whoever choose, I trust those kind of manufacturer, provider, or TE vendors, and they can do that. I give you that mutual trust scheme, right? Here we define a scheme, right? Who offered, whether Qualcomm will provide or not, I don't know personally.
So maybe I should try respond. So Qualcomm obviously provides different roles in the ecosystem. So it's obviously a hardware manufacturer, but it also provides implementation of a secure world operating system. And so it's definitely an important stakeholder, which is why we, in preparation for the BOF, we obviously reached out to the companies who develop the hardware and also some of the components. And so far, they went negative. If I sort of can relay that conversation, they had some additional use cases, offline usage of the protocol that they wanted to address, and there was a post to the mailing list about this topic. Whether they then will, when the work is finished, and deploy it, that's obviously we hope so. But the future is somewhat unpredictable, always. So we do our best to involve the right players.
Yeah, but I understand. But I mean, you're asking, in my mind, a fairly significant financial commitment from the entities to actually manage all the certificates for all the devices in a unique way, right? Because they actually have to tie their manufacturing back to a CA that actually gets managed and certified and authenticated and checked and audited and all of the things to do that. And has anybody signed up to write the check?
Yeah. So there's obviously a downside in using a PKI compared to a symmetric key solution, which comes with this. Of course, you don't need to operate your own CA necessarily, although many of the device vendors actually do. In the meanwhile, even for IoT devices, we are sort of recommending our partners to sort of use some credentials provisioned to the devices, understanding that there is some cost tag, price tag to that. But there's also an added value for security, and it's not just something that we do here in this effort now, but it's something that we, in order to improve the security of applications and devices, we recommend in general.
Okay, I will close my class now after this.
Yeah, I think that's just like good. We call it basic practice, right? The root of trust, right? If you want to ensure device is genuine, right, you can remotely trust it. You have to put the root of trust. What root of trust? What certificate helps that? As an analogy, I say URCC, right? It's GSMA, URCC SIM card now, they all just try to also recommend all certificates as a device certificate so that I can remotely do the validation. So I think the manage the device certificate is not that hard, or maybe it's a cost, but it's a necessary step, in my opinion.
Marko Żurowski, NCSC. I have a comment about the use cases that we saw earlier for using the TEE in a mobile phone as an authenticator device for mobile payments or for enterprise authentication. It seems to me that there's some overlap here with some work that the FIDO Alliance has been conducting over the last several years. I believe they've been addressing a similar problem. I understand that the work of here is somewhat wider, but if that authentication case is kind of like a main driver, then I think there's some work to do to reduce the overlap with the work of the FIDO Alliance.
Okay. And there are probably many people who can answer that question in the room because you see Jeff and others who work in the FIDO Alliance. So in a nutshell, the answer is the FIDO developed protocols could be an application that is used to actually dump it there to provide faster rollout of FIDO-based device or FIDO authenticators to mobile phones. That's my perspective on that. So it's actually a consumer of the technology rather than like competing it. But there are probably other authentication mechanisms that one could roll out as well more easily.
Yeah, authenticator application is one for the good candidate of this. That's also a use case, right? That one has an enterprise use case, actually. Okay.
Yunfei Kupai. From the developer's perspective, it makes sense to have such work that will make the to lower the threshold for the developers to develop such applications. But I am wondering from the smartphone vendors' perspective, if such standardization will in the meanwhile to lower the threshold of the developers' selection will increase the security threat to their smartphone. So this is my concern.
So sorry, what is that? A comment or question?
The mic lines are already closed, but I actually think I want to get to the charter focus polls now.
We only have 3 minutes.
We have a couple of minutes, and we are losing cookies if we don't go there like in first 3 minutes of the break starts, and that's very important for security. So we have a couple of questions we want to ask. We actually want to know. First of all, is that does this group actually now understand what should be done? If the actual what is going to be, what is the protocol going to be, what parts of it is still something that is going to be decided in the charter, but do we have a feeling that what is so I want to get a hum for this. So I will first ask how many people do we have an AD? Okay, so all right, so the first question is going to be how many people actually do people think that we don't understand enough what this is going to be? If you think that we do, hum now. All right. Okay. How many people don't understand what is this going to be and think that we should think about this more? How now? That was quite even, which means. All right. So to think more people actually understand.
Yeah, on this side it was a little bit even.
Yeah. All right. So, but wait. So we don't have a clear, consensus on this.
Sorry. Yeah, this side of the room has sounded a little bit stronger on the first, but not convincing.
Not enough for consensus.
Yeah, not convincing.
Yeah.
So do we actually want to go to the last two questions then? If we don't have
If we don't have consensus.
If people don't know what we are doing.
How about to know if we should just continue on and this is BOF number 1, right?
Yeah.
So they have an opportunity to firm it up. So it might be interesting to just get a sense, even with some hands, right? So we know how many people are going to be, pouring some time into this to help shape it into something, right? That'll help.
Okay, that would be actually a good question. Another question is how many people are actually interested in working on this, topic and reviewing, writing documents and so on. Put your hands up now.
Actively.
I think we have about 20 or something.
No. More like 12 or 15.
I think there was more. Put your hands up.
Put your hands way up.
Oh, actually, no, we're getting up to 14 now.
I count 14.
14 or, okay, 14 or 15. Okay, so
Okay.
all right, but I don't think we actually. Is there anything else we need to ask?
Thank you. I know we'll just wrap up, but we'll just continue on the list and see if we can shape up something for another BOF in Prague. And you can always get a BOF, move to a working group between if there's momentum and energy.
If you haven't signed the blue sheets, I think they're over by the projector. So sign it now. Thanks. Thank you. Yeah, there were nobody. Yeah. Yeah, I mean, Michael explicitly asked if anybody had questions, and well, that was interesting.